All right, looks like we're there. So, 8 billion biometric users of WorldCoin. At least that's the aim. I'll explain what all of that means soon, but the topic will be secure multi-party computation that we use to achieve that. I'll start with a quick overview. I'll brush to how we use linear MPCs because I assume most of you are already familiar with linear MPCs. And then I'll deep dive a little bit more into the specifics of our solution and in particular the scale that we're operating at, which will be interesting. But before we go into that, a quick overview of what is WorldCoin, because not all of you may be familiar. Some of you might be surprised by this shiny metal sphere that I put out there. And the TLDR is that we are working on solving the problem of how do you know what is a human being in the digital domain. And the way we're solving that is by having this hardware device that has all sorts of sensors that can verify that something standing in front of it is a real live human being. And in addition to that, it can help create what is known as an iris code, a biometric that is derived from the human iris. This is incredibly high entropy, and this can be used to not only verify that the thing in front of it is a real human being, but also that it is a unique human being, which is a very useful primitive to have. Once this is done, this attestation is attached to a public key. This public key is entered into an anonymized set that lives on Ethereum. And from that moment on, the user, through their wallet, can create zero-knowledge proofs that they are part of this anonymous set. And using these proofs, they can engage in all sorts of actions. Why do we need unique humans in the first place? It's kind of, in my opinion, the biggest missing primitive in blockchains. There's a lot of stuff we can do currently, but once you start developing more complex DeFi products, you'll quickly find yourself being limited by not having a concept of an individual on chain. Specifically, anyone can create as many accounts that are indistinguishable from each other on a blockchain as they want. But people want fair airdrops. You sometimes want a token to be distributed equitably amongst a large set of people. What is happening now is that people are experimenting with more and more complex methods to establish who are eligible people and make sure that they don't game the system. And on the other side, people are finding more and more sophisticated ways to game the system. In my opinion, the end game here is that we just have a primitive of what is an individual and then be able to use that to build airdrop mechanisms on. Another area is social consensus. We have ultimately consensus algorithms are in some sense subjective. And here you also want to have a concept of what is a human being and who is behind certain decisions. And that quickly leads to governance. The governance primitives that are currently being used on chain are all based on token ownership. And the problem with token ownership is that this gives you governance influence proportional to your stake in tokens. And this is not always ideal because it gives particularly the wealthy a strong advantage. If you want to have a different kind of governance mechanism, for example, one where you have one person, one vote, or even ones where you have quadratic voting, you need some kind of way of recognizing individual human beings. So these are the main areas where this comes into play in the blockchain world itself. Outside of the blockchain world, we are now very clearly having problems being able to distinguish content created by real humans from content created by bots. This was actually quite prescient from WorldCoin, I would say, because they started working on this 6 years ago, when this was definitely not as clearly the case as it is now. But I think it validates the thesis. And I believe that as we get further and further into the digital domain, We just need to have this concept of a human being that a lot of these things can be anchored on, especially stuff like being able to prove things about you, being able to prove things about your reputation. Also being able to do that in a very strongly privacy-preserving manner. And in the end, the way to do that with the highest assurance is by linking it back to the individual. Now, why biometrics and why iris codes? There are alternatives out there, and those were explored and dismissed. One of them is you could use passports, ID documents. The problem there is that they're not as inclusive as you might think. A large part of the world doesn't have an ID document that is digitally signed. And on the other hand, a lot of people have multiple of them. So this doesn't give you quite the amount of assurance that biometrics do. Then a question we often get is, why not fingerprints? They don't have a lot of entropy. A fingerprint or even face recognition is good for the authentication use case. Meaning, let's say you have a device that you own, it knows you, and it wants to make sure that you are in front of it. Or a door that knows 10 people, and those 10 people are allowed access. Then you have a one-on-one matching. If you want to recognize uniqueness, you need to have an N-on-N matching. So this is quadratically harder than the authentication use case. And even fingerprints only scale to about 1 million people. Once you have about 1 million people in your set, every new entrant will match one of the previous existing entrants. Something similar goes for face matching. Irises, however, have an enormous amount of entropy in them. It's not genetic, so even identical twins will have completely different irises, which makes them kind of ideal for this particular use case. And they have some other advantages as well. Irises require dedicated optics to see, and you need to be actively engaged in the process. It is not something you can just scrape from the internet or like take a picture from someone from a distance or lift off a glass that they had in their hands. It is something that the person needs to actively participate in. This gives it an amount of additional assurance. It's also something that turned out to be kind of relevant later on. It's also easy to associate an iris biometric to a face biometric, which has some use cases where you want to do an additional authentication later on, where you don't need the high entropy, but you still want to make sure, hey, this was the same person that originally signed up. Then, in order to do this, yes, they are. And actually, to get to uniqueness with the quadratic complexity and 1 billion users, you do need the entropy of both, because you're still kind of cutting it close. But biometrics are kind of scary, they're sensitive. We want to be very, very respectful of that. So we employ a ton of privacy and trust enhancing technologies. And we even layer them on top of each other. There's multiple defenses that protect your anonymity, which kind of start with the zero knowledge proof that you ultimately use to prove that you're a unique human being, which reveals absolutely nothing other than your membership in this set. So that's the first layer of defense. And then there's other layers of defense under that. The one I will particularly go into is the MPC. Now, high level, how this system works and how these technologies tie together is you have this user. The user goes to an orb. The orb verifies that it's a live human being and takes a high resolution picture of the iris. Then, through a QR code, you provided a public key. It will then encrypt the image with this public key and send it to your device. So essentially, the orb is just a fancy, trusted selfie camera. And now the user has a hardware authenticated signed picture of their own irises. They then produce a zero knowledge proof that turns this raw image into a bit vector, which is the biometric template. Then with a further zero knowledge proof, this bit vector is turned into multi-party shares and encrypted for the individual MPC participants. The user then sends these MPC shares encrypted to each party. Each party verifies the zero knowledge proof. So the parties only learn that they received a correctly computed share from an authentic orb. They then engage in an MPC protocol that establishes uniqueness. Well, actually, before that, they engage in a TEE protocol to make sure that everyone is running the correct version of the protocol. Then the MPC protocol guarantees uniqueness. Each of the three parties signs off on it and signs off on the public key that the user generated and provided and sends the signatures back to the user. The user now has 3 signatures on his or her public key. And with that evidence, they can insert their public key in the anonymous set on Ethereum. To make this scalable, we provide a CK Rollup-like service that can insert 1,000 of these users in a single transaction. But the basic concept is that we try to maximally decentralize it by putting the user at the center of every operation. The user is in control. It's the user interacting with the orb. It's the user interacting with the MPC. It's the user interacting with the blockchain, and so on. The other thing that is very important to us is that besides the user, no one ever sees the raw biometric data. Everything can happen in the encrypted domain. And this is the quite amazing achievement that MPC unlocked for us. Again, a little overview of all the technology that's involved. I already mentioned the orb. It's a human, it detects humanness and creates this iris image. It also produces a so-called HIRAX commitment, a cryptography-friendly image format, so to say. Then we have an AI team that is working on the specific algorithms, how to go from this image to a particular kind of vector that is useful for these matching algorithms. We use what we've called zero-knowledge machine learning to be able to create zero-knowledge proof of this derivation path. Then we use MPC to do the matching algorithm that's necessary. This is not an identity matching because, as you might imagine, if you go to the same orb multiple times, you don't get the exact same vector, but you get one that is close enough according to some distance metric. And that is the thing the MPC needs to assert. Then we have a trusted execution environment that the MPC runs in that provides a second layer of defense. Then, as we'll get into later, is that we're working on a vector database to make the MPC protocol scale better. Right now, we're still doing a linear scan. Then we have what is known as Semaphore, a zero-knowledge protocol for anonymous set membership, and what we know as Merkle Tree Batcher, which is a CK rollup style mechanism that allows us to manage this anonymous set on Ethereum. There's a lot of really great teams involved here. A particular shout out to Tassio, who helped out a lot with the MPC implementation. I think here we can be rather quick because I think everyone here is familiar with the matter, but we actually started out then in FHE land, and we didn't get to linear MPCs until a couple months into our R&D effort. I think in part because we were mostly familiar with Giles Garbutt Sickets, and that just seems completely infeasible for what we're doing here. But once we learned about ABY3 and linear MPCs, things started to make a lot more sense for us. And this quickly became our pick, in particular in the semi-honest setting, where the performance is actually suitable for our use case. Now, in the semi-honest setting, you need to have another way of verifying that the protocol is executed correctly. Fortunately, in our particular use case, the thing we care most about is privacy, because this is the guarantee we want to give the user. The correctness is important, but it's not going to hurt the user directly if the correctness fails. So here we are okay with a not information theoretically proven guarantee, and instead rely on trusted execution environments to get the correctness of the protocol. Now, quickly going into how the Iris code works. In the end, after all the processing is done, this image is turned into a 12,800-bit masked bit vector. Masked just means that you have the bits themselves, they can have 3 values. They're either 0, 1, or uncertain. And the matching is basically taking a so-called fractional Hamming distance, where you take all the bits. If you have two of these masked bit vectors, you only look at the bits that are unmasked in both bit vectors, and you compute the Hamming distance between those, and divide it by the number of bits that was unmasked. The exact equation is right there. That is a binary equation, and we want to compute this in MPC quickly. One thing we've realized is that if we encode this essentially ternary value as -101, then we can compute this fractional distance that is here in pop counts as an inner product in a field or ring of sufficient size. And it basically becomes this expression. Of course, you can move the fractions to the other side and basically just get something that works in the integer domain. I can skip over this. But basically, inner products in linear MPCs are super, super nice, because you can do all of the products locally, accumulate them, and only then do you need to do a round of computation to sort of reset them to replicated sharing or a low degree polynomial, depending on which exact MPC scheme you're using. And given that the bit vectors that we have are 12,800, this gives us a 12,800 improvement in our MPC complexity. It's massive and absolutely necessary. We've looked at replicated secret sharing in the 3-party setting and Shamir secret sharing. It's not over booleans in the sense that you need to compute this pop count, which will result in a number. So, a 16-bit number, correct? Yeah, so we basically had kind of a matrix of choices. We could use replicated sharing over the ring of 16-bit integers, or we could do Shamir secret sharing over a sufficiently large field, so like a 16-bit prime. Now, we need to, before I go any further, I think it's good to know the scale that we're operating at. This is actually slightly dated, but let's say we have about 13 million users, of which more than 6 million are verified using their Iris biometrics. These verifications happen at around 1 per second on average, and they can go up to 10 per second during peak hours. And we need to design the system to support 20 verifications per second for the next couple months at least. In terms of how much memory this takes to store, 6 million users, 6 million humans, 2 eyes per human, 2 vectors per eye because of the bit masking. You end up with 12,000 elements. You have 12,800 elements per vector, 16 bits per element because they are secret shared in that ring. And you need 572 gigabytes per party. And because of the intensive nature of the processing, all of this actually needs to be GPU memory. Compute, 6 million humans again, 2 eyes, 31 rotations. This is something specific to iris codes, but the iris is kind of has like a rotational uncertainty in it. When you have different iris codes, you need to rotate the iris slightly and try different rotations and see if any of them match. So every match basically turns into 31 individual matches. Each match takes 2 dot products, one for the one to compute the intersection and one to compute the intersection of the mask. Each dot product requires 12,800 multiplication operations, just local ones. We're not talking about communication yet. And we need to support 20 verifications per second. So this is just computing these distances. This is not yet doing the threshold comparison and turning the matching results of the 31 times 6 million matches that you're doing into a single unique, non-unique Boolean vector, which is another operation. But this actually turns out to be the dominant one. Compute-wise, these inner products dominate, even doing a Boolean OR tree over 6 million entries, or doing all these millions and millions of threshold checks. This alone takes 400 tera field operations per second. In terms of network complexity, kind of you can do the same derivation. You'll end up at the end, when you have computed these pop counts, you need to reshare them in order to do the further processing. That step alone ends up, no, actually, you have 16 bits that you need to communicate in order to get this distance through the MPC parties. And then there is a further 240 bits of communication complexity to do the threshold matching, where you say that, hey, I've matched this iris code against this iris code. Is the distance larger than this value? That takes most of the communication complexity at 240 bits. Add all of this up, and you'll need about 4 terabits per second between all parties. Before we decided on the approach, we did a lot of benchmarking. We started out with Graviton 3 instances, which is what we've used successfully for a previous version of this MPC setup. The funny thing is these ARM-specific cores have dedicated opcodes for vector dot products in the 16-bit ring. So these were nearly ideal for the replicated setup. We did find a bug in LLVM where it didn't produce this opcode correctly, which we got fixed. Then we also benchmarked GPUs, A100 and H100, which are the previous and current generation of NVIDIA. Actually, I think they released a new one recently. There we found a bug in CUDA itself where when you computed so it doesn't support 16 bits directly, you need to turn it into 8-bit operations, and then the 8-bit dot products are accumulated in a 32-bit accumulator, but they accidentally made that a 32-bit float instead of a 32-bit integer, and you're losing precision that way, which was not great, but that was also fixed. And then we could benchmark on the GPUs as well. If we look at these, and then we look at the different options that we have here, where we have our replicated ring, or Shamir shared field, and we've also looked at slightly larger ones because they make the remainder of the protocol easier, because for the threshold comparison, we actually do need to lift it to a 32-bit field. Turns out that despite their incredibly high price, the H100s are just so ridiculously fast that they're still the most cost-effective option. So that's what we went with. And in particular, these P5 40x large instances that AWS has, they have their own hardware, and it differs from the hardware that NVIDIA provides. And the difference is that they dedicated more PCI lanes directly connecting the GPU to the network interfaces instead of the GPU to the memory. So your GPU memory bandwidth is lower, but we're not planning on using that anyway. And instead, you get more GPU to network bandwidth, which is something we use a lot. So that allowed us, by leveraging direct GPU to network communication and completely bypassing the host memory and host CPU, allowed us to actually get to the terabits of throughput that we need. Now, that's a lot of scale. And the way it's done currently with this linear scan through the database doing all this matching, obviously is not going to get us to 1 billion users. Not in this approach. In fact, it grows more or less quadratic in the number of users because the number of signups also grows linear in the number of current users. And yeah, we need a better algorithm. So what we're now working on is hierarchical navigable small worlds, which is a vector database method. The nice thing here is that it's an approximate nearest neighbor search that only uses a query is A or B closer to C internally to implement its database. We more or less already have this query on our MPC setup, so we can just build the index structure on top of that. And at least in an initial version, we're not going to worry too much yet about any path dependency that is revealed, but it would be interesting to look into how that can even be made private as well. But this should turn what is currently a linear scan into something that is logarithmic complexity, which would bring us to 1 billion users. All right. Thank you all. Do we have time for questions still?
Yeah, can you say something about fingerprint vein as a biometric factor? Because there's some recent research whereby people are claiming they have way better entropy over there. Have you done some analysis before deciding what you're gonna use as biometric factor?
Yes, we have. We've looked into all of them. Actually, the closest competitor is palm prints, and this is what Amazon is, for example, using in their Go stores.
So what was the argument against the vein?
Fingerprints, as far as we've seen in the research, just don't nearly have enough entropy to be able to do uniqueness verification on a billion people scale.
Yeah, not the fingerprint, the vein. I mean, there are people whereby they are looking into building 3D cameras. That's the fingerprint vein as a picture.
Ah, veins. Okay. No, we haven't looked into that in particular. Part of what is actually challenging with fingerprints is it's not as easy to do liveness checking as it is with iris codes and face. Like a biometric in itself is not that useful. It's just a piece of information, and like your fingerprints are all over the place. They don't demonstrate much. What you really need to do is make sure that this fingerprint is attached to a real live human body. That is quite easy when you have face. You can use depth sensors, thermal cameras, multispectral cameras, and so on. With fingerprints, those devices are quite easily circumvented in my experience. And also, if we want to combine it with a face image, for irises, this is easy because they're in the same frame. If this was with a fingerprint, then there are more attack factors where someone might be just standing behind me, sticking their arm through my t-shirt, and the orb would have no way of figuring out whether that attack is happening or not.
Hey, hi. Thank you for the talk. Here. So, what is the estimated cost for each user in your new solution? So, this running the MPCTE is going to be costly, right? So,
Yes.
what is the approximate cost for each human ID generating the zero knowledge proof and getting the user's public key added to the Ethereum? Like, what is the estimated cost using the login solution?
Very low, because every user only needs to go through this system once. And a uniqueness check basically takes a second on this system. The system is expensive to operate, but that's mostly because of the very high throughput that it happens on. We have like thousands of signups per hour, so on a per user basis, the cost is actually not that high.
I see. Okay, thanks.
All right. Please give it up for Remco.